Hi, welcome. Welcome to Java 1. How many people have made that joke today? Probably everyone. And Oracle's probably live streaming this, so I apologize. So my name is Chris. I work obviously at Twitter, so I have the Twitter shirt. And so this year, so last year I was giving a presentation about how we use Graal at Twitter, how we introduced it. Basically, it was a story of the first year of me being at Twitter and what we've done and the improvements we saw by using Graal for our microservices. And so this year, I'll be talking about how we tune our services and then how we want to do this on a continuous basis. Okay, so I'm going to talk a little bit of, I hope not too many people are here because of machine learning, because I have no clue about machine learning. I just put it in the title because it's cool. No, we're using it, but it's not something I have to touch, right? So it's kind of this black box thing that we'll be talking about it later. So, but basically, this is the next step of improving our services with Graal, and we see a lot of graphs later, so that's the part I really understand. The other thing, we'll find out. Okay, so most important question of the day, as always, who in this room has a Twitter account? Yeah, that's good. That's probably 60% or something. So you are the people, you create one right now, because this is the first day of Oracle Code 1, and so you have to tweet a lot about all the other sessions you're going to. And you also have to tweet about this one. And if you're going to tweet about this one, you should add that hashtag TwitterVM because we at Twitter, we have our own VM team. And last year I was standing up here and I think I said it's a small VM team, but that's not true anymore. We grew in size. I think we're 8 people now. And there are different people involved, like we have a bunch of GC engineers, then there is me, the compiler engineer, then we have a Scala expert, we have an architecture expert, a person who is working on AUTOTUNE, for example, and so on and so on. So we grew, and so we can try all these things. How can we run our stuff better and save money at that time, right? So I'm not talking about the money part this year. The people who don't know me, I worked on JVMs for a very long time, 14 years on compilers pretty much, and I used to work for Sun Microsystems, and then Oracle acquired Sun, and I was always part of the Hotspot compiler team, so I was working most of the time with C2. So maybe I should ask a bunch of questions. It's not a very technical talk anyway, but do people know what a JIT compiler is? Yes, hands up. That's not too many hands, okay. Oh no, it's getting better. People know what C1 and C2 are? The compilers in Hotspot, okay, yeah. So I was working on C2 most of the time, very painful. And so the 3 major things, the biggest projects that I've worked on while at Sun and Oracle was probably JSR 292, so Invoke Dynamic, I worked on that. Wrote a bunch of the compiler support, and so that it actually runs fast. And then we had basically 2 different implementations. One was a lot of handwritten assembly code. It was impossible to maintain. And then we decided to move a lot of that logic into Java land and into the package Java lang invoke. So I wrote a bunch of this Java code as well. And if it doesn't work, you could technically blame me, but other people have touched the code after me, so they broke it, and my code was fine. Then for JDK 9, we did CHEP 243, which is the Java level JVM compiler interface, and that's coming or was coming out of the Graal project. So Graal is a JIT compiler that's written in Java, so it needs an interface to talk to the VM that is written in C++. And so we extracted that interface, kind of standardized it. It's not a standard API, but it's kind of stable. And we put it in a JDK 9 module, and then you can plug in a compiler, an external compiler. And then also in JDK 9, we did 295, which was ahead of time compilation. And that feature actually uses Graal, and then JVM CI as well, to AOT compile code. So it's basically a small command line utility that loads in Java classes and then sends it over to Graal. Graal compiles it, and at the other end, it spits out a shared library. That's what it does. So you can do that since JDK9. And now work at Twitter. Best company on the planet, really, I love it. So I don't think I have to go into too much detail what Twitter is. I think most people know what it is. So it's already a little older. This is like 2 years ago. But these are all of our microservices, okay? And then you see the lines between the services tells you which service is talking to which. So we have tons of services, right? But even more instances of these services, right? We have a bunch of very important services, like there's the tweet service that reads and writes tweets. So we have many instances of that one. We have a social graph instance that takes care of all the, the edges between the users, who follows who, and so on and so on. And we have a timeline service that builds up your timeline, and so on and so on and so on. So these are the bigger ones we have. Then we have smaller services that produce shortened URLs, all these things, direct messages, and blah, 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 whatever you need. That's what it looks like. And it's a heterogeneous hardware. So obviously, like, we have our own data centers, and then we have different platform types and so on. So there are some issues, and this is all this talk and my work is always about performance, and so it matters on what hardware platform you run and so on. Good. So performance optimization, I think, I'm hoping, let's put it this way, I'm hoping everyone in here is doing it at some point, right? But the problem is always when you do it by hand, it doesn't scale, right? Even you can do a few parameters, and then you read up on them, and then you try them out, and they all depend on each other. Well, maybe not all, but a lot of them depend on each other. So if you change that one, the other one is affected as well. It's very time-consuming and labor-intense. And the problem with that is you do it once a year, once every 2 years, once every 3 years. Someone at some point feels the need to do it, does it, and then that was it. Right? And until someone else comes along and feels the need to do it. But in the meantime, your code is changing all the time, right? The thing you've optimized for, it's long gone. So the upgrades of your code makes this optimality fleeting. It will disappear, right? So this means that many, many services, even at Twitter, operate below optimality. Yeah, you've optimized for this particular change set at some point in time, but that was 3 years ago. So you need something that's constantly finding the optimum. And that's where this whole tool that we are developing at Twitter, where this one comes in. So performance tuning, so this is the part where I'm going to talk a little bit about how it's done, what Bayesian optimization is, and then later we will see 1 million of graphs, roughly. So you have a function, f, and it's defined over a domain x, right? And then you want to find a configuration that maximizes f, either whatever f is, throughput, or in our case, the way I always look at the data and the graphs we see later, we want to reduce things. We want to reduce garbage collection. We want to reduce CPU utilization, and so on and so on. And these configurations are always subject to constraints, right? You have to meet certain constraints. When you tune parameters, right, when you look at, let's say, hotspot JVM parameters, they have certain default values. And they work fine. And if you go crazy, right, and let's say, and you bump up the inlining level by plus 100, it will not work, right? You might even have problems to start up your application because it's just inlining so much, it's compiling so much that it doesn't even run. So you have to have some constraints to make sure what are you actually tuning or trying is still valid, okay? So this is basically how it works, right? In the manual case, you pick a parameter to test, well, I don't know, inlining size or I don't know what, and then you run it, and then you look at the outcome, and then the engineer says, well, okay, yeah, that was not an optimum, maybe I try it a little bit this way and that way. What you really want is to replace that engineer with a black box. You don't even want to know what it's doing or why it's doing that. It just should do it. And machines are perfect for this, right? That's where the machine learning part comes in. Okay, so optimization of a black box function. there's something called Bayesian optimization, and it's a method to learn potentially noisy. That's very important, because what I said is, if you go too far with your parameters in either direction, it will probably won't work anymore. So that means it will become very noisy. And it does that iteratively, very efficiently, and it finds the optimum in a few iterations, whatever means a few. We'll see how many I did later, and you can see that it looks like sufficient. Okay. So it works well with nonlinear, multimodal, high-dimensional functions. That's also important because we don't want to tune one parameter. We want to tune many. And so your n-dimensional space, the exploration of that will become tricky. So I'm a JIT compiler expert, right? So people in here probably could tell me what Bayesian optimization is. But Romke, one of my colleagues, he's an expert in this. He worked on that stuff. There are at least 2 YouTube videos of talks by him. There's one from Java 1 2016 already. So we've been working on this tool for quite some time. And then he gave another updated version of that at Devoxx last year, I think. So if you're interested in that and the more detail I'm going to talk about, you should watch this stuff. And I'm briefly going through this because I would like everyone to have at least an understanding how it works and how we find the data points. So when we look at the data later, it's a little better, so you can understand it a little bit better. So we're just assuming we are tuning this parameter at the bottom, whatever it is, doesn't matter, and then we have the performance on the y-axis and higher is better. So we did 3 experiments here, right, and it looks like this. And you could assume, okay, yeah, maybe it's like a curve that goes like this, because it seems like it goes that way. But in fact, the true function looks like this. I mean, we're making stuff up here, but we just assume it looks like this. And so what Bayesian optimization does, it has this space that it thinks what it looks like, and that's that. And when it has a point, you can see it narrows it down to actually where it's supposed to be. And so it uses this blue space for its explorations. That's again, the true function, what it really should look like. And then it picks, that's the optimum we have right now. Okay, and then the blue part that's above the optimum you have, that's where Bayesian optimization will pick new points to run an evaluation. Okay, so at the bottom you see the graph that says expected improvement. That's basically the curve of the blue part above the red line. And then it will pick the one that has the highest. So it's the second bump you see, right? So we do an evaluation here, and we found out, oh, it's actually worse than the other one we had. And then that's how it explores the space of possibilities, okay? So it picks the one in the middle, this guy. Yes, he's okay, slightly better. There's one on the left now, so we try that one, it looks like this. And so it goes through the space and explores all this expected improvement over there. We think it will be much better, but actually it's much worse, right? So, and that's how you go. And then eventually you find this one, and then you try the last 2 ones, and then you have the optimum. And that's that one. So that's the theory behind how this works, right? You send out, it will pick not really random values for you for the parameters, and then it sends the information back, and you run the experiments, the evaluations, and then you find the points and look what's the optimum, okay? That's all I'm going to talk about this, because, but I think it kind of, I hope you can now understand how this roughly works. So we like Bayesian optimization because it's non-parametric and it's robust. That's very important for us, and it's extensible. That's very important to us. And it has been used in many other different use cases. So because we want to do, this should not be, a researchy thing. We want to have this on, we're not there yet, but that's the goal. The ultimate goal is we want to have this on in production all the time, right? The services we have, they should be auto-tuning themselves all the time, right? And that's the goal. So we need something that's actually really, really stable. Okay. Now we're getting to the part where I know more about. So what is AUTOTUNE? That's the tool we have. We call it AUTOTUNE. You have something, it's a Bayesian optimization as a service, right? So we have a service running somewhere that does the Bayesian optimization thingy that we just talked about. We use wet lab for that. At some point, Twitter bought the company. There's, I think, an open source version that wet lab is based on. I think it's called Spearmint, if I remember correctly. I would have to look it up. And then AUTOTUNE is a driver that runs these different experiments for the explorations that are suggested by the Bayesian optimization. So we get over, please try this, this and this and that parameter, and then run an experiment and let me know how it went. That's basically what AUTOTUNE does, okay? What is Graal? I think most people know. It's a Java virtual machine just-in-time compiler that's actively developed by Oracle Labs. There's an OpenJDK project for it. There's also, the source code lives on GitHub, so you can download this and try it out. Graal, as I mentioned earlier, it uses JVM CI, and it's written in Java. It's not very important for this talk, but it's important if you want to try it out. And all of my talks that I'm giving are pretty much about Graal, and one of the main reasons why I'm giving these talks is because I want you to try it as well. You're going to see how much CPU utilization we save by using Graal, and I think that other people could have this advantage as well, and so we want to make Graal more mature, a more stable compiler, but for that to happen, we need other people to run different code, right? I always say you can only run spec-GBB so many times until you have explored all the optimizations you can do. What you really want is to run the shitty production code that you guys have and find all the bugs. That's what you really want. So I have a talk, the Twitter's Quest for Holy Grail runtime, that talk, I show all the bugs we found when we started Twitter services, when we started running Twitter services on Graal. We found bugs, yes. We found about 4 or 5, but that was it. And then since 2 years, no, nothing. So we need, please, when you go home, after Oracle Code 1, try it out. Yes, if you want to learn more about Graal, there's this talk, it's called Graal, How to Use the New JVM Compiler in Real Life. That's where the is written in Java part comes in. So when you go home or to work and you try Graal, you should know a few things. And the most important thing is that it's written in Java and just has different properties today than a compiler that's written in C++. Number one, it has to be compiled itself, right? It's kind of a meta-circular thing, so you have to be aware of that. Number two, it allocates memory on the Java heap instead of the native malloc heap, right? These are the two main things you have to know. For example, if you're running a benchmark or something, or if you look at the metrics for whatever application you have to keep that in mind, that it's just behaving slightly differently. Okay, so when you watch this talk, I do tons of demos in that talk, so you just see how to use it, where to get it, how to use it, how to turn it on, what to look out for. I run a bunch of benchmarks, and so on and so on. So watch that one. Okay, so we want to tune inlining parameters. That's what I would like to do, and in this particular case for Graal, we are tuning these 3. The one is called trivial inlining size, so that means if you have a method that you want to inline, and the size of the nodes of that method is less than 10, then it's just inlined. Because it's so trivial and so small that the compiler assumes it's probably worth inlining it. So it doesn't even look at profiling data or anything, it just inlines it. Then there is something called a maximum inlining size. Up to that number of nodes, it's actually would like to see if it can inline it. If it's above that, it doesn't even do it, okay? And then there's something else called small compiled low-level graph size. So that's another threshold that basically drives inlining a little bit. I don't want to go too much into detail here, but so these 3 we want to tune. And so the default values is 10, 300, and 300, okay? So in my Twitter's Quest for Holy Grail runtime talk, at the very end, as you can see already here in the screenshot, I did this manually because I wanted to see if we can actually squeeze something out of Graal above what we already get by just using Graal. So I really sat down and did it manually. And I just show you 2 graphs from my previous talk, and this one, where you can see parallel scavenge cycles. And we could reduce by just using Graal. You see at the bottom which compiler it is. So the orange one and the green one is Graal. And so Graal just reduced scavenge cycles by 4.2% just by using Graal, okay? And then I fiddled around with these 3 parameters manually, and I could reduce this by another 1.5%, okay? So you can do it manually. It totally works, but you will never find the optimum, right? And the same thing for user CPU time. So user CPU time, but just using Graal, we reduced it by 13%, and then manually changing the flags gave me another 2, okay? That's nice. Took me a couple hours to do this. Was not a lot of fun, really boring. And I'm very, very sure that I did not find the optimum because I was randomly picking things, right? So I don't have a Bayesian optimization built into my brain, so we have to, try something else. These are 3 snippets from the configuration file that AUTOTUNE takes. It's a JSON file, and then you say, okay, there's this parameter, and it has a type of integer, and I want you to try from minimum to maximum. So when we go back, we saw trivial inlining size was 10, and then 300, 300, okay? So I decided we do, because the trivial inlining size, if you make it smaller, it's probably not going to give you better results. So we just start at 10, and we go up to 25, whatever. And then the other ones, we go a little bit below and a little bit above. So we go from 200 to 500, and the other one, because I thought with the small compiled one, we need to go a little bit higher. So we go from 200 to 650. That's how I started out the first time. You could also, and I've tried this, and it totally works. I just didn't have the time to finish it up for this talk, but you could say 0 to 1,000. Doesn't matter, because you have constraints, and if the constraints are violated, the evaluation is not valid, and it's just kicked out, right? So the test setup, as always, I have dedicated machines to run my experiments, and these instances, they all receive the exact same request. That's very important because a tweet request, for example, a tweet can have 1 character at 280, right? And so the memory allocation for these 2 tweets is very different, but we want to compare apples to apples. So then we are using a slightly older already Graal version, but it's still fine. And we use the default tiered setup with C1 and Graal. So we still compile with C1 in the regular default way as you are running your application with Hotspot is you compile with C1 and C2 in tiered setup, and we compile with C1 and Graal. All right. Experiment 1, tweet service. So the tweet service is a Finagle thrift service. Finagle is a framework that we open sourced. It's an extensible RPC system for the JVM used to construct high concurrency servers. I have no idea what it does. I don't need to. The important one here is Finagle itself is 92% Scala code. Okay, so most of our microservices are written in Scala. Only like a handful of services that we have are actually written in Java, and everything else is written in Scala. That's important because for the benchmark numbers we are going to see later, Graal can optimize Scala code really, really well. Good. So for the tweet service, we use this objective. It's like this query language we have is called CQL. It doesn't really matter. As you can see, it takes the user CPU time in seconds, right? And it does an inverse function of that, 1 divided by that, because we want to optimize it. AUTOTUNE optimizes things or looks for the maximum, but we actually want to reduce CPU. So it's an inverse function of that. And then we're coming to the constraints that I was talking about. For my experiments so far, I only used 1 constraint. We should actually be using much, much more, but again, there was not enough time for me to do all this. But in this case, we're using the constraint that makes sure that we are not getting throttled. Okay, that's something that our Mesos or Aurora, whatever, again, I have no idea what it does, but you want to make sure that's not happening. And if it's happening for, if the throttling is higher than 10, that's something my SREs told me, is that, no, it's higher than 10, and it's not working. So that's the constraint, okay? You could have 10 constraints, 100 constraints if you wanted to. And we should have that, by the way. Okay, so this is an AUTOTUNE run, okay? So this is requests per second for 24 hours. I was running for roughly 24 hours, the experiment. And you can see it's a period or an evaluation run is 30 minutes. You see it runs for 30 minutes, then it, shuts it down and restarts it, and then it runs again, and so on. In this graph, you don't see a lot. You just see, okay, this is the distribution of requests per second over a day, right? Well, something really important was happening on the left, and then it was boring on Twitter. This is, for the same time, the user CPU time. And you see the experiment on control, and you can see, I don't have a mouse here, but you can see when the blue is below the orange, that's better, because we're using less CPU in that case. And so these are the evaluations, and then AUTOTUNE, will pick the good ones. This is the same graph, just a little bit different. You can see when it's below, then it's a good run. If it's above, it's not as good. This is what the AUTOTUNE results look like. So I was running it for roughly 24 hours. I did 44 evaluations. And this is the outcome. The objective is 1.08. That means, because it's doing a maximum, it's 8% better than the control, right? Like playing Graal without modifying the parameters. So we reduced the CPU utilization by 8% in this experiment. And it's these 3 parameters that it found: the trivial inlining size 21, 486, 590. So I think it was, what was it, 10, 303. Oh, I have it here, right. The one was going from 10 to 25. And so the default for the first one was 10 and 300 and 300. So the experiment or the evaluation here tells us, okay, they are too low for this particular service, right? If we look at the bottom of this table, you see there are 3 where the constraints were violated. So they didn't run well. Something was wrong with them. And then you can see there were a bunch of experiments. I can't show you all of them, but there was one that was 5% worse and 3% worse and so on. So it finds that optimum. We can look at this in a chart as well, and that's what it looks like. You see the trivial inlining size at the bottom. Remember that this is not just this value of the trivial inlining size. It's a 3-dimensional space, because you always run an experiment with 2 other values as well. So you can't really look at this graph. It's impossible to plot this out 3-dimensional, but at least it tells us, you see, it's slightly better when it becomes bigger. It's like performance gets better. And we can see that with the maximum inlining size roughly as well. It's more like a flat curve, to be honest. And then here, it's very clear, right? The bigger this one gets, the better the performance gets. And then what I did to verify that this is actually true, I was running a verification experiment to see if it really works. So I took the first line, I took the parameters that were found by AUTOTUNE, and then just ran the service for 24 hours and looked at the data, and this is what it is. So we have, again, 3 runs. We have a C2 run, we have a Graal run, and we have a Graal with the AUTOTUNE found parameters run. And you see they are all the same, so they all receive the same requests. Scavenge cycles again, so we would like to reduce GC activity. This is always good. That means we don't allocate as much memory, and then pause times and P latency times are affected by that. And as you can see, just by using Graal, we reduced that by 3.4% for the tweet service. And then this is AUTOTUNE, and it's another 3.5%. And that comes up to a total of about 6.97% improvement, 7% less GC cycles. It's great, right? If you don't have to do GC cycle, it's amazing. And the cool thing about this one is, if we would be, we do today, right? Today, we do the orange line, right? We just use Graal and that's it. But if we tune it, we can double the improvement. So this is basically the same graph, just a different metric. This is allocated bytes per tweet. As you can see, it's a very flat curve, right? It's again at 3.5%. And with the AUTOTUNE experiments, 3.4, so it's really the same. This is really a Graal better escape analyzing object allocations and reducing garbage that's being produced on the Java heap. Okay, user CPU time, same graph, same time frame, 12%, but just using Graal. And then there's the AUTOTUNE result. And we saw an 8.3, 8.4-ish improvement in AUTOTUNE. That translates in a real scenario to about 6.2. So we are not exactly sure yet why there's a difference. One difference could be that my evaluation runs were too short. I only did 30 minutes, right? Because I wanted many experiments to explore the space, but 30 might not be enough. But still, 6.2 comes up to a total of 18%. We could reduce the instance size of the tweet service by 18% machines. That's a lot of money. It really is. Okay, very interesting, P99 latency, because that means how quickly can we send out requests. And we can also reduce that one, most likely related to less GCs, and the code gets tighter if you don't have the object allocations and so on and so on. So it's hard to see how much it is in this graph, but what we can do is we can integrate over the whole, over all of the 24 hours, and then we see how much it really is. And it's about 8.1% that we could squeeze out by running AUTOTUNE. So 8.8% better P99 latencies. That's amazing. Experiment 2, because I usually, in my other talks, when you go to watch them on YouTube, you'll see I always use the tweet service because it's very easy to run for me and I kind of already understand how it behaves. But I thought, okay, this time we should throw in a second one to make sure it's not just the tweet service that's doing so great. So we're doing the same thing with the social graph service. It's also a finagle thrift service, as far as I know. I'm not 100% sure about this, but it's this is the mission statement from one of our internal websites. It's an abstraction for managing many-to-many relationships at Twitter, right? So it's doing user things, whatever. Again, doesn't really matter what it does to me. Objective, same thing, right? We want to reduce CPU utilization. So it's the same query. It's just a different name of my instances. In this case, it's called social graph. And the constraint is again the same. We want to reduce, or we don't want to see throttling happening for too long time. There's always a little bit of throttling happening at the very beginning of a run, and that has to do with you're compiling a lot at the very beginning, right? And with Graal, you're compiling more at the very beginning. So there is, I don't have a snippet for that. Maybe I should put it on the slides as well. There's something in AUTOTUNE where you can say, oh, please ignore the first 2 minutes of the run, because at the very beginning, so much stuff is happening, and it's not really representing your actual load. And then later, the last, 28, 25 minutes, it really does stuff. OK. Same request per second graph, just a different day. It looks like this. Okay, you can see, again, the 30-minute runs. And here, the graph with the user CPU time. It's already very nice to see the difference between them. And again, in this view, it looks like that. It really goes up and down, when it explores the space, as we've seen with the graphs at the very beginning. Sometimes Bayesian optimization thinks, oh, I could find something here, and then it's way worse. right? Here, at the very end especially, you would assume it always finds points that are better, but that's not the case. So these are the results. Objective 7.59%, trivial inlining size 23. I can't remember now what it was for the tweet service. I think it was 21. Maximum inlining size of roughly 400, and the small compiled is 650, so, or 646. That's very interesting, actually, the last one, because it's very close to 650, right? So maybe 650 was a bad choice on my part. Maybe the 1 to 1,000 would have been better in this case. And I should rerun these experiments again. The bottom of the table looks like this. We had one that violated the constraint. The other ones, I don't know whether there are 3 in progress, don't ask me. But we went down to about 6% worse. That's already quite a bit. Good. The charts again, trivial inlining size looks like this. Not that interesting, to be honest. And the maximum inlining size looks like that. And compiled low-level graph looks like this. This one always seems like a higher number would be better here. As I said, 650, you can see it's like at the very top here, at the very end. Okay, social graph, same thing, verification run. Requests per second for 24 hours. And social graph is using CMS. So we are looking at part new cycles now. And the improvement you get for social graph here by just using Graal is only 1.6%, right? It was better for the tweet service, but still 1.6% is 1.6%. If I don't have to do the GC cycle, that's always good. And then AUTOTUNE looks like that. You can see that's already a nice improvement. And that's another 3.5 to a total of 5.1%. So the improvement by Graal itself here is much, much less than the improvement we can get out of it if we actually tune the service, or for the service, right? Then user CPU time is just 5.5% to compare 12 that we had for TweetyPie, the tweet service. And AUTOTUNE then could get this gain, and that's another 7.8, and that's really nice. So the AUTOTUNE on the user CPU time here got more than just Graal. And that's a total of 13. And that's a 13% improvement is already great. So I don't even know how I run with time. So questions. And before someone asks a question, I ask myself a question. Because I think, yes. I know. I do this for a little bit longer. I know what you guys are asking. Did I do the same thing with C2? What's the outcome of that? Well, yes, of course I did. You think I would come up here and just do it with Graal and not do it with C2, and you could ask me questions I can't answer? No. So let's look at C2. I picked these 3. They're kind of the same as for Graal. At least these are the ones that are the closest. So max inline level, that's always an issue. Most people even, I think, know about this one, that the max inline level is 9, and then it just stops inlining. Max inline size is 35. The difference between C2 and Graal is C2, the 35 is bytecode size, okay? Graal, it's nodes in the graph. That's very, very different. So if you ever had an issue of a small method not being inlined anymore, you should look if you have some assert statements in that method. Because C2 is so stupid, it just counts assert statements as well. And we never fixed it. Don't tell anyone. I think it's live streamed, by the way. So, and inline small code is 2000. Inline small code is the one parameter that screws up most of your inlining when you run with C2. And the way this works is it's timing dependent. So if C2 finds out that you already have C1 compiled code for a method, and it's greater than 2,000 bytes, it does not inline it. And depending on the order of your compilations, The C2 compilation might happen before your C2 or after, and then your inlining is completely different. That's why sometimes it's very, very difficult to get 2 runs with C2 with the same performance numbers. Inline small code, that's it. So we're tuning these, and I decided to do pretty much the same thing that I was doing for Graal. I pick a range. I go from 5 to 20, from 10 to 50, and from 500 to 4,000, right? Because I thought this one, if I increase it to 4,000, that might actually help and get better performance numbers. All right, so another AUTOTUNE run, right? So we see same thing, nothing new. It looks like this. Yes, it finds some improvements here and there. So, and then again like that. That one looks pretty big, but it's actually not that big as it looks like. So what we could get with C2 was a 5% improvement. Okay, that's pretty nice. Inline level 16, very interesting. Default is 9, right? If you look at the top 6 here, it looks like we should double it either way, which is very difficult to do it because it's over the years, C2 has grown with its heuristics, and if you change it now, the whole world will be affected. So very tricky to do this. Inline small code, the top and the second one, very different. So maybe it's not that important. And the max inline size, yeah, it fluctuates a little bit, but it's not that bad. Bottom, we didn't have one that had the constraint violated, but interesting is that it found some that were much, much worse because 87 is like a 13% degradation of performance. That's a lot. I was surprised by that. Doesn't mean anything, but I'm just saying. This graph, very nice, right? You can see, okay, up to 16, 17, it's good, and then after that, nothing's really happening. It kind of looks like as if the curve actually goes back down again. But 9 is the default, and so for this service, for this code, I'm not sure if it's representative for the whole world. Again, remember, this is Scala code and not Java code, but it definitely 9 is not enough. Then this is inline size. I was also surprised by this one because it's basically flat. As this one, this is also pretty much flat. And we've seen, as I said earlier, like the first two, it was 3,000 and then 1,500. And we can see here, yeah, it doesn't really make a difference. It's just this one outlier here a little bit. But again, it depends on the other two as well. All right, that was C2. So maybe I should add a slide here, another one that, so we could get, what was it, a 5% improvement with C2 in the AUTOTUNE experiment, which probably will boil down to a little bit less, maybe a 4% improvement in if I do an evaluation run, which I didn't do for C2. That's still not even close to what we can get with Graal, right? So just by using Graal, you can already win a lot on Scala code. I have to, again, remember you about this. But then the AUTOTUNE works much better on Graal than on C2. It's just the way inlining is implemented in Graal. If you tune the parameters, it just can do much more than C2 can. All right, summary about this. It's a summary that I use for all of my talks. It doesn't really fit for this talk, but I thought I'd use it anyway. And it's that. Because I really want you to try it, right? I mean, what I've shown you, we do this. For the tweet service, we actually use these numbers already in production, right? We turned it on manually. Basically, we put it in the configuration when so we already get that gain. We save that money. I'm just showing you what you could potentially save, right? And as I said earlier, one of my goals, and there are some other people in this room as well, our goal is to make Graal the default compiler in OpenJDK. And for that to happen, we need to show that the compiler is actually mature enough to replace C2. And for that, I need everyone's help. We at Twitter, we run fine. Since over a year, 20 or so, and 4 or 5 of our most important services run on Graal 100% in production. So if you tweet something today, it runs through a bunch of services that it's all compiled by Graal. And we didn't have an issue since. But we need other people to try the code as well, to try Graal as well, so that we find the remaining bugs that are in there. Because I'm sure there are some more. There are certain things, we found issues because we were using agents, for example, and things like that. So please, 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 try it. You could go to your manager and say, well, look at this presentation. We could potentially save a lot of money. That's always good when you go to managers. But please try it. Thank you very much. And I'm not sure how much time do I have left? 0. Yeah, ask me questions outside.